Hi everyone, welcome to the Stats and County Ontario Applied Education Seminar, a joint initiative at the Ontario and Department of Statistical Sciences. Those of you who are statisticians will know that over the past sort of 30 to 40 years, as we've seen the rise of sort of applied statistics, that's very much been accompanied by a rise in the importance of coding. Very few of us have been trained to write code. However, there is a whole branch of a science, science that has expertise in this and have been developing approaches for writing code that does what you think it is doing over the past number of decades. Our guest today, Caroline Lemieux, is an assistant professor at UBC in the computer science department, and she's an expert on writing code that does what you think it's going to do, as much as anyone can be an expert.
Yes.
She holds a PhD from the best, one of the best universities in the world, Cal, Berkeley. And she then worked at Microsoft Research in New York before studying at UBC. So it's a great pleasure to have you here, and thank you very much for coming all the way over.
Thanks so much for having me. Yeah, so before I get into automated testing, just to set the groundwork of what motivates my research. So you may know that software or code still has bugs. Even though increasingly there's large language models that claim to write code, like when humans do stuff, they usually make mistakes. And I think large language models are also going to make mistakes. So software continues to be written with bugs. And this is kind of unfortunate because software is becoming increasingly pervasive throughout all different aspects of our lives. And so these bugs can have increasingly severe consequences. Just to give you a sense, over the last 10 years or so, there's a number of bugs that are important enough that they've had logos and news stories written about them, essentially because they've been such important security vulnerabilities that they cause issues to the broader public other than just coders. But beyond the bugs that are so famous that they get logos made about them, we also know that behind the scenes, the cost of poor quality software is quite bad. So there's this estimate from the Consortium on IT Software Quality that the cost of poor quality software in the United States alone was around $2.8 trillion in 2018. So if you broadcast that cost to, the whole world, because the US is not the only part of the world, and in 2023, right, those costs are going to be much more severe. So in my work, I try to build tools that help decrease these costs. My work kind of focuses on doing that via three main areas of software engineering research. That's automated testing, specification mining, and program synthesis. And I also have some recent work that uses machine learning in conjunction with these automated testing tools to try to improve outcomes there. That should give you a broad overview with some keywords. But what I'm mostly going to talk about in this talk, given that the audience is not all computer scientists, is kind of the basis of why automated testing is something I find cool, and kind of the baselines, what from my research in it I think is kind of the most important baselines to know about. So today I'll actually start with an appetizer of just talking about testing software in the first place and why that's something we want to do. And then I'll talk about random automated testing and when bugs are really bad and how some more sophisticated automated testing methods can be used to find these really bad bugs. And in the conclusion, I'll also kind of give some broader strokes of where my research fits into all of this. But a lot of this is educated by just having worked a lot with automated testing tools. Let me hide this if I can. Okay, it's just kind of ugly, but there we go. Okay. So for an appetizer, let's talk about the testing software. And also, if there are questions, things that are sufficiently unclear, there are numerous points where questions might be natural, so feel free to bring them up if you have questions. So let's talk about something that I hope you never actually have to implement yourself, but for a simple example, let's talk about, say you're given an assignment to build a function that sorts a given list in ascending order. So say you have a list of these integers, you can think of what it would mean for this to be sorted in ascending order. And hopefully you'd figured out that that's, negative 27, 1, 3, 34 is the sorted version of this list. So what should we do before we start implementing this? Well, the gold standard of test-driven development, which essentially no one follows, but is a nice gold standard, is that before you write code, you write tests first, and that these actually help you figure out what the code is supposed to do. So in this case, this is pretty straightforward. We already had one example of what sorting meant. You can think about what it would mean to sort this list, which is completely reversely sorted, right? It should be sorted completely in ascending order. And if you're in computer science, you probably also want to think about corner cases quite a bit, like what happens when I have an empty list or a list of size 1. Those are both already sorted. And if I have an already sorted list, then I should also, okay, now I figure out when the clicker stops working. I should return that already sorted list. So it's essentially like high level idea of how tests would work here. So again, you should probably never implement sort on your own, but if you did, you might want to implement, say, merge sort, which is known to be an efficient algorithm. And the way that that works is that you start with a list, you split it up in half, you split those up in half, you keep splitting those until you get sorted lists, aka lists of size 1, which are by default sorted. And then essentially all the work of merge sort comes in putting those back together as in a, I should really memorize this keyboard shortcut, but it takes 4 characters. Putting those back together in a sorted way. So that's kind of the high level of how merge sort works. This is not CS 101, so I'm not going to get into all the details, but just to give you a sense of what's going on, essentially the way that that corresponds to some Python code is that if the list is of size less than 2, yeah, it might be useful to make me not host on the, okay, perfect, thanks. If the list is of length less than 2, then you just return the list because it's already sorted. If it's not, you're going to take the midpoint of your list, which is like the length divided by 2. And in computer science, we like to start counting from 0 rather than 1. So first you take the elements from 0 to the midpoint for the first half of the list, and the second half is the rest of those. Then you recursively call merge sort to merge both halves of that list. I was talking to you about how to implement merge sort, which, as I said, you should never be implementing sort on your own. That's kind of the idea. All the code we need to kind of have an idea about what's going on for the rest of the examples. And actually, most of the complication of this code is actually in the merging of 2 sorted lists. But again, this is not CS 101. I'm not going to tell you how to implement that. Interested reader can look at that for themselves. So we have an example implementation here, and now we actually want to see, does this do what we expected to do it? So one way we can do this is we have our tests, which first we've encoded in kind of this casual way, but we can encode those in an executable way. If you're not familiar with Python tests, essentially these are just defining functions with the name test empty, et cetera. And these assertions are statements which will fail if the thing that's being executed there doesn't work. So in this case, these will fail if merge sort doesn't give the thing on the right-hand side. Okay, and we can see how these work. If we open good merge sort.py, that's like kind of big. Anyway, just to tell you, it does here the merge is there. This does what I had on the slide. There's some tests here. And if we run PyTest on this, all the tests pass. If I did something stupid, like turn this J here into an I don't really know what the consequences of this would be, but I would presume that it's bad. Everything fails, right? So if I have a typo in there, it catches it, which is quite nice. And if I rerun it now, stuff, that's interesting. It's interesting to note here that when I added that typo, actually only 2 of my tests failed. So you're already seeing that writing one test on its own isn't going to give us everything we need here. So that's the essential motivation behind just testing is you have this set of things that you can run to assert that your implementation behaves as expected. So say we do something funky here, which here I'm taking the length of the list, and I already took that length of the list up to calculate the midpoint of the list, and say that for some reason I'm concerned that this might be expensive. It actually isn't in practice, and you shouldn't do this, but let's say for some reason I'm concerned about this. I could say, hey, well, I already took the midpoint, so the length of the list, so I could replace this by length of the list by midpoint times 2. And now I would ask the question, is this change okay? I don't know if there's any folks in the audience that have any idea of whether this change would be okay or not. We can go see what, yeah. If you have negative of, no, you can't, the length is not going to be negative. Yeah. Yes, so definitely if you have an odd length list, this is not going to work. So kind of a detail, but that length of the list div2 is essentially doing integer division. So if you have 7, then this would return 6. Which is not what we want. We don't want to cut off parts of the thing, or otherwise the sort isn't going to work. But we have a pretty nice test suite, so let's go see what it tells us here. So I'm going to open a file, that has that change, which is, the file is called, this is maybe a bad omen, but it's called bad merge sort. It has that change I mentioned, that we changed this from length to midpoint times 2. And let's go see whether our tests catch this. All tests pass. So we just reasoned that they probably shouldn't all pass. In this case, all our tests are actually even length. But let's say that we hadn't put in the mental effort to reason about what went wrong. We might be at this point thinking that indeed this change is okay from our test suite. So that's not optimal. So this brings me to talk a bit about random testing. So back in 1990, there was this paper published in the Communications of the ACM, which is the closest to say kind of a general journal of computer science. And one of the authors of this paper, remember this was 1990, was logged into a remote computer from his home machine. And since it's 1990, internet was over a dial-up. And that means it went over phone lines. And it was raining. And rain on the phone lines caused random characters, like random keystrokes, to be sent to the machine that he was using. And that wasn't too unexpected given how phone lines work. But what was surprising was that these random keystrokes that were essentially being pressed via rain on the phone lines were causing programs on that remote machine to crash. And the author of this paper thought, that's not great. I would like my programs to not crash, if it's raining. And so he built this, along with the other authors, built this tool called fuzz. And I'll use the term fuzz test for the rest of this to talk about a particular brand of automated testing. But kind of here, the idea of what fuzzing was that you have this source of randomness and you have a program that accepts files. And you call that source of randomness to generate random characters. Until one of these sequences of random characters, so like a file just consisting of random data, essentially, causes the program to crash. And that was the initial idea behind fuzzing, is you send totally random stuff to the program under test. And this, unsurprisingly, found a bunch of bugs in software that was quite widely used at the time. And there's an updated version of this paper for 2020 where this is still unusually effective at finding bugs in software. There is a problem, though, here, which goes back to our merge sort example of what if the program takes in a more complex input. So these programs we were looking at here are ones that essentially just take in a file as input. But say in our merge sort example, right, we took in a more structured thing like a list of integers. If you're processing files in data science software, you might take in like a CSV or some other kind of structured file format, which needs to have commas delimiting things. So in those cases, sending totally random sequences of characters is maybe too close to garbage to be interesting from a testing purpose. But you can still kind of use this concept by replacing that source of randomness with an input generator. And I'll show you an example of this for our lists. But essentially, the idea is that input generator is a non-deterministic function that each time you call it returns a random input in the space of reasonable inputs. This is also, I call this generator-based fuzzing. It's also known as property-based testing in some of the programming languages and software engineering literature. So let's see how we can apply this to merge sort. So we saw that we had made a change that passed all our unit tests, but we were somewhat suspicious about this result. So let's see how we might automatically test this with random fuzzing. So first thing, we'll have a generator of random lists, which creates random lists of integers. And we're going to send that to the merge sort. So we're essentially going to evaluate merge sort on that random list. Then we're going to check whether there's a bug. If there is, we'll show the user the result. If there's not, we're going to generate another random input for some number of times. So this is great, but this is actually kind of challenging. How do we actually know if there was a bug? What does a bug mean? So on the tests we kind of had this notion of what it meant to be correct, which was we as humans thought about each input and thought about what output we would expect, given that we have this idea in our head of what exactly sorting should do. Can we generalize this, though? Like if we're given an arbitrary input, how can I arbitrarily tell you what the output should be? That's the reason I'm writing an algorithm in the first place. I, as a human, don't want to be writing the output for every single input, right? In the case of sorting, you could actually rely on if you have two implementations of the same piece of software that are supposed to do the same thing, you could compare their results to each other. But sorting has another nice property, which is that it's actually something we can kind of formalize semi-mathematically. So if you think of this assignment to build a function that sorts a given list in ascending order, what properties should you have on the sorted list? Or are there properties about the relationship between the input list and the sorted list that we expect have to hold? I'll give a second for any thoughts on that. The next one must be larger than the previous. Yeah, so each element should, that's actually something we can check mathematically. There's some other things too, like the return list should be the same length as the input list, and it should contain all of the same elements. And then, of course, the sorted property should hold, right? So again, starting from 0, for all the indices in the list, we want the current index to be less than or equal to the value at the next index. So that's quite nice, actually. And we can write this property in code. And I got lazy writing this code, and I'm not going to check for this second thing. But we can at least check the other two and write a function that checks whether the sorted list is same as our original list. So first, or is the sorted version of our original list. So first, it's going to check that the lengths of the two lists are the same. And then we're going to go through that sorted list and essentially check that other property that each index is less than or equal to the next one. And that gives us a check. Any questions on that? Okay. So now we can actually implement this random fuzzing as code, right? So this notion of was there a bug we can make more precise by actually inserting our check sorted here. So we're going to call merge sort, we're going to get a sorted list, and then we're going to call check sorted. If there's an assertion failure, we'll report a bug to the developer. Otherwise, we'll say there's no failure and go back to generating random lists. As for generating random lists, there's a lot of different things you can do. In this case, there's no particular constraints on what I expect my data to look like, other than it's a list that contains numbers. So I'm going to choose the random length for the list between like 0 and 10, and then add random integers between -1,000 and 1,000 until I reach the expected length. So if we go back to our merge sort thing, where we're not sure we've covered all possible cases in our tests, we can actually do some random testing now. And this brings me to demoing. So I have something called random test merge sort here, which first we're going to test the good one. Essentially, this does what I had on the slide. The actual random test code is quite simple. Essentially, what you're doing is 100 times you generate a random list, then you call merge sort, and then we call check sorted. And if 100 tests pass, we're going to say we're OK. Otherwise, something will happen. So if I run this, did I save that? This is the problem with using this particular code editor. So we do that on the original merge sort implementation on all 100 tests passed. So that's not the one that had the bug. If I now go and make this the one that had the bug, so essentially now when we call bad merge sort, it'll be the one that's okay. So now it'll test the bad merge sort. And so if I call this again, we're going to get a failure actually kind of immediately. Is this an interesting case? So the input list had 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So yeah, as we said, it should fail on odd length things. That one's also length 7. Okay, anyway, you get the point. Even though if I repeatedly run this, I keep getting different random lists that have the wrong return value. This one's kind of nice, actually, right? Like it's a pretty minimal example. If we just have 3 elements, we're only getting 2 of the elements back, which is, this would be a really bad, you really wouldn't want to use a sort function on your data if it discards like half of your data. So this change is not okay. We saw that it fails on like any like odd lengths list. For the list of 3, it got rid of 1 element. Actually, this is like a very tricky bug where this code works as long as your list is a power of 2 long, because essentially this recursive call to merge sort means you throw elements away, even if you're like, if you have 6 elements, that ends up being sorting 3 things, so you end up with a list of length 4. So yeah, so that's kind of the basics of what I consider the most fundamental automated testing. And this kind of automated testing is actually pretty powerful. But unit testing is way easier to rerun repeatedly, and it's way easier to encode what correct means for a single input. So the techniques are really complementary. You shouldn't really discard unit testing based on this one weird bug I have where the unit test didn't find it, but the random fuzzing did. But there are some words of caution here. In order for this kind of random testing to be effective, you need 2 things. One is you need to be able to encode correctness in a programmatic manner, which we could do for sortedness. As software becomes more complicated, the notion of correctness might be hard to encode in any other manner than like the piece of software I'm implementing it. But if you have some higher level mathematical properties, you can kind of encode those in correctness checks. And the second thing is that your generated inputs need to be quote unquote valid. And I'll give an example of that. So for this first point, right, if I hadn't had the assertion about checking the lengths of the list, The lists I was returning were still sorted. It's just that they were missing elements. So I could have randomly fuzzed that and found, called this on hundreds of things. And we wouldn't have found the bug in our merge sort change if I hadn't had that assertion on the length of the list, right? And that might create this random testing, might create a false sense of security where you think I have unit tests, I have this random testing, everything should be great. But like if you haven't thought about this carefully, you might get a false sense of security of this is not actually correct. And for the second point, say that instead of testing sorted, like sort, we were testing insert sorted, which is essentially taking a sorted list and adding an element to it and maintaining sorted order. So essentially, it's something that's only interesting if your input list is sorted. You might test this by having this, the thing you're going to call repeatedly is you're going to check whether the list is sorted. If it's not, you return early. If it is, then you actually try to do the insert and check whether the list is still sorted after the insert. And if you have a random generator like the one I did, where I just generated random lists totally arbitrarily, you'll only ever test the case where the input list is not sorted, because you can think of the probability of randomly generating a sorted list by selecting random integers. It's not going to be very high as the list is greater than like length 1 or 2. So you could run this on like 100 inputs, but always hit this first return statement. And again, you would kind of get a false sense of security there. Any questions on what I've covered so far? Yeah. 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 So yeah, this is like really challenging. Yeah, this is like a common drawback indeed of this kind of generator-based fuzzing. I'll talk a bit briefly about some other things, some other kinds of random testing that don't have that drawback. But yeah, essentially this is the big disadvantage with anything that's generator. So it is really powerful if your generators are good, but depending on the side of data your generation, that could be really hard. Like say you're testing like something that takes in images, right? How do you generate a random image? Like, what does that even mean? That is actually really challenging. So there does need to be some kind of domain knowledge of like, what reasonable values do you expect here? And you are going to be prescriptive in that. But this also depends on like what the goal of your software is. Like if the goal of your software is to not like fail for correctness reasons, like here, it's kind of okay to be a little more prescriptive to the point where these are kind of the data distributions I think I would expect. Again, the whole point of the randomness is that it finds bugs that you wouldn't assume there. But again, it depends. Like, whereas some of what I'm going to talk about after this is like software where you actually have security implications of it. And for those, you'd want to lean on the sense of being much less prescriptive because you're assuming essentially an attacker model. So that is my really long answer for no. Like there aren't like really like general guidelines. It really depends on the domain that you're pulling from. But there are things like generally like oftentimes small inputs will be enough to show the problem. Like you don't necessarily need to be generating lists of length 1,000 to find this issue. But yeah, it's a very relevant question to the practical use of this. Yeah. Oh, yes. Yeah, I forgot to do that. But the question was about whether there were any guidelines about writing the generators. Yeah. Cool. There are some tools for this. A bunch of them are called, I don't know if these exist in R, whatever, but like in Python, there's hypothesis, and it's called quick check in a whole bunch of other languages, this kind of generator-based, property-based testing stuff. You can also build your own, like if you're not too complicated here. If you can build your own generator, you can, write that loop. And it's not too, that's the nice thing about this type of random testing. Any other questions? Okay, I'll talk about the not fun stuff or the fun stuff. So what we've talked about so far is like correctness bugs, or what are called functional bugs, where essentially these assertions are really particular to the intended behavior of the program under test, right? So these assertions for sortedness are useful for checking a function a program that sorts things, not so useful for checking a program that does something totally other than sort, right? So we can't use this to check the implementation of red-black tree, which is some silly data structure. But as I talked about earlier, I talked about bugs that have large consequences, and just to kind of motivate bad bugs, I'll talk about heartbleed in particular. So heartbleed, I'm getting really old because this was a problem in 2014, so I should have a more current one, but heartbleed was essentially about the software that governs, the safety lock you see in your browser. So in 2014, this was mostly powered by OpenSSL. And that was used everywhere, and heartbleed had these consequences of like the Canada Revenue Agency had to shut down its website in late March because it was vulnerable to heartbleed, and there were still 900 social insurance numbers stolen from that website. And a later article says that this hit a lot more government computers than previously disclosed. So this was a pretty bad bug. And what caused it was a really common bug in C programming. And to talk about that bug, I'll need to talk about strings. So in Python and most high-level languages, a string like hello is represented as, this is Python, the string is 5 characters long, right? Hello has 5 characters in it. The first is H, the second is E, kind of how you would expect things. In C, hello is not represented like that. C just knows that the string starts at this memory location on the computer, and then it asks the user how long it is, and it's like, oh yes, the user said it's 5 characters long. It is 5, so I'm going to start there and count 5 characters, and that's my string. So this is not great. Essentially, the reason this was an issue, and I am stealing from XKCD here, the way that this secure connection thing works is that there's a point where there's a heartbeat, meaning that the server you're securely connected to, and you communicate to make sure like, hey, are we still communicating? And that's called heartbeat because it occurs periodically. And essentially the way that was happening is that there was this exchange of these C strings. So the user would say like, hey, server, are you still there? If so, reply potato, which has 6 letters. Server's still there, it replies potato. But the problem here is that it was trusting this value provided by the user. So the user would say like reply bird. Obviously they wouldn't reply bird and potato, right? This is the thing. It would say like reply bird, which has 4 letters. Server says bird back. But it was just trusting those values provided by the user. So if the user said something like the user was actually malicious, they might say like reply hat and say that that has 500 letters. And the server just kind of trusted that and then leaked all the next 500 characters after hat. So that's essentially how those social insurance numbers were able to be leaked. So that's a high-level view of how heartbleed was bad. It's an instance of a really common bug. It's called a buffer overread. There's this whole database of software vulnerabilities. This is a common weakness in software. There are many other common weaknesses in software that are related to this bad use of essentially C strings. The nice thing, because these are really common, is that we were talking earlier about how you had to write manual assertions for correctness in your software if you want to say check sorted or check some other property. For these types of bugs, there exist automated assertion inserters. So essentially, you can pass the software into these automated assertion generators. It adds these checks in the software so that, let's pretend this is the structure of the messages that were sent in this heartbeat. The structure is actually not human readable, but let's pretend it is. For a normal message, the software wouldn't complain at all. But with these checks inserted, if you sent that bad message, this would cause the software to crash automatically. The reason these checks aren't built into the software when it's deployed, because you say, well, yeah, why don't we just do that there and the software will crash instead of leaking stuff, is because these generally slow the execution of the software down, and you don't want your software crashing arbitrarily in general. And then the question gets back to the same question that we had with the random testing, which is how do we find inputs that trigger this bug? So that gets me to this. So could random fuzzing have found heartbleed? Probably not pure random fuzzing, because random fuzzing was like just sending pure sequences of random characters. And OpenSSL would have probably said, like, that doesn't look like a message at all, and I'm out before getting to that buffer overread. So what could you do instead? From the first part of my talk, you would say, write a generator for well-formed messages. And that is still what you should do if you can't actually write a generator for your data. But sadly, people are often like, this is too complex. I don't want to write a generator for this. So the second thing is you can start somewhere sensible and generate inputs that are close to that sensible input. So instead of going from a source of randomness, we're going to start from a well-structured input. This is just a generic XML thing. And then we're going to mutate that input. And the default mutations we have in these tools treat that input as just a string. And so the mutations are just adding kind of random characters to the input. And this is what's called mutational fuzzing, because rather than generating a whole new input each time, you just mutate it from an existing one. So there are tools that do this. Essentially, the core thing with those existing tools, though, is that the inputs are modeled as byte sequences. So essentially just like raw strings on your computer. And the mutations treat the input as byte sequences with no regard for structure. So you could probably do something in a case where, like, regarding the question of like, how do you write a good generator? You could, instead of writing a generator, it might be easier for you to write a mutator. So like, to say, like, I expect this data to be within this range, and I'll like randomly add some noise there and see if the thing is robust to it. But the tools as they exist are kind of working at a lower level. They're not modeling the logic of the data, they're just modeling it as random bytes. So these tools are still useful and are still finding bad bugs in software, which really tells you software is terrible. And I am scared when I get on a plane. The other problem, there's another problem here, though, which is there's kind of no progress here. So you'll only be able to find a bug if they're like one step away from the original input, right? So you might have a bug that, so you're always starting from one input, and you might have a bug that like, oh, you need to add some random noise here and some random noise here and some random noise here before you actually see the bug emerge in your software. So the most kind of complex form of these automated testing algorithms, right? Okay. Thank you for the animation. The most complex form of these algorithms kind of start to resemble something that's close to what we call a genetic algorithm. And just to give you a real high-level sense of how these work, they look a lot like the mutational fuzzing algorithms. You start from a set of reasonable inputs to your program under test. You pick one of those and mutate it slightly. And then you execute your program under test. And this program has been compiled in such a way that when you execute it, you don't just get the result, but you get some more detailed feedback about the behavior of the program. Kind of a way to understand that is if you have if statements in your program, you get feedback of like which side of the if statements was covered, because programs kind of execute differently based on the sides of the if statements that are covered. And then if you cover one of those new interesting sides, then you save those inputs to your set of initial inputs. So kind of a more abstract way of doing this is to consider this is that you've added some stuff into your program. So it tells you when you have different behavior in the program under test. And you save inputs that have new behavior, with the idea that you don't want to save all the inputs because that would just explode. But if you have one that causes your program to do something slightly different, then you save those. And these are super, super powerful. They found tons of real world bugs in things like Adobe Reader and Firefox, LibreOffice, if you're into that. I think the iOS kernel. So like, anyway, tons of bugs. These are the ones that are important enough to be security vulnerabilities. And just to give you a sense of the impact of these, so Heartbleed happened before the adoption of these modern fuzzing tools. And we talked about how you had this issue with the CRA in Canada. In the US, there were millions of patient records that were compromised at a hospital chain. Part of the reason it had that bad impact is that even though it was introduced in 2012, it was only discovered by the good people nearly 2 years later. right? So by that point, this software was super widely adopted, including all the government computers and all this stuff. So what that meant is that that bug was actually exploitable. So even though it was fixed 6 days later, in the interim, there was a chance when attackers could use, because it was on like literally every computer. So 2 years after Heartbleed, there was another bug introduced in the same software library, which was actually judged to be potentially worse. And the reason it was judged to be potentially worse is because in addition to just revealing memory, as we saw in the other case where you're like saying hat and then a whole bunch of secrets, this bug could have led to the execution of arbitrary code. So essentially, an attacker could have caused arbitrary code to run on your machine, which is not good. But we never had a logo or a news story written about this bug because it was discovered 1 day after its introduction by a modern fuzzer. I don't know how long you take to update your software on your computer, but 1 day was not long enough for everyone to have updated the software to this new version that was buggy. And so the costs were quite minimal because essentially it was fixed right after. And even better would have been if the developers of this software had run the fuzzer before making the software public, which they now do, because then, you know, there wouldn't even be that day of potential vulnerability. So there are a bunch of tools to do this. Yeah, I'm happy to chat about those in particular if it's of interest. There's essentially, this works well by default if you have programs that take a single file and command line, which you probably don't. But it's like quite straight, like you just, if this is your regular command, like my command, my file, you can just paste it like my command at is my file. Otherwise, you can use this in like Python and stuff. And sorry, this is C or C++, I guess. And it's essentially, this is a program that accepts a string as input. So these two parameters are just the C style string, where it's a point in memory and then the size of the string. And then you do something interesting. And what I just want to talk about here is demo how cool this is. So here's a test program, which is dumb. It takes in the string. And what it does is it checks that like the 0 element is H, the first element is I, and the second element is exclamation point. So, and if all of those hold, this will cause a bug to be, like a spurious bug to be triggered, right? So essentially on any input that starts with hi exclamation point, this will fail. So the probability of triggering this with random strings of length 3 is like 6 times 10 to the negative 8 of like you generating that exact random string. So if we run this for at like 10,000 executions per second, if I did this math a while ago, so I might be totally off, but that should take around 1,600 seconds, which is some number of minutes, that like half an hour, like around half an hour. Okay, so since that will take half an hour to do with random testing, let's start running that. It's not actually going to take half an hour, but okay. So yeah, so I have what is this called? So I have essentially that code in that file. I'm making stuff difficult for myself by trying to memorize things. All this is doing is compiling the code. Okay, so all that I've done there is I've essentially compiled this code, so now I can run it with a fuzzer, and I'll start the fuzzer. And I said that if we were doing randomly, that should take half an hour, but it found an input almost immediately. And if we go look at that input, it is the input hi exclamation point. So essentially that algorithm that's checking if stuff is interesting is doing a really good job here of automatically finding that input. And we can make that slightly more complicated. Like that was only, 6 times 10 to the negative 8. Of course it's going to find it. Here's a harder one where we're checking hello. So 1/256 of random generating. Chance of randomly generating that. Let's see how long it takes, because really it's kind of boring. I just ran a thing and then it immediately just printed a bunch of garbled text on my command line. So in this case, it printed more garbled text. So it just executed, I guess this one is optimized to be really fast, but it just executed like 440,000 inputs to find that input that I think should also say hello. Yeah, so it's hello, and then there's some garbage afterwards, because essentially it would just fail the first time that you find that hello. The reason I talk about this example is, you're probably not writing code that just does that, but it is quite impressive how much better that feedback loop can be for testing code than just pure randomness if you don't have a meaningful notion of what it means to generate input. This is just kind of a cute story that some of my work is combining the generator-based testing with this kind of evolutionary loop. And we did this for Java, and we were writing a paper, and we wrote a tiny little test to put in the introduction of the paper to be like, here are the tests you can write. And rather than taking a random string, it takes in this data structure, a map, and a string, and it's checking this thing. And we just wrote it as like, here's our small little example. And then we ran it, and it found a real bug in Java. So software that hasn't been tested in this manner is highly likely to fail. Whether or not that matters depends on what I was saying earlier, whether you care about this from a security perspective or from a correctness perspective. So I'll close, and then I'll have time for questions. Most of my work is really innovations. So that's kind of the baseline of what I consider the most important things to know about automated testing. In my work, I mostly aimed on improving these fuzzing algorithms. As I said, I mentioned by combining like the two kinds of fuzzing I mentioned, by finding performance bugs with fuzzing, throwing in like reinforcement learning to try to improve this. That didn't really work, but yeah. But what I'm kind of interested in going further is kind of the problems around the adoption of these automated testing tools. So if you're not writing software that takes a single file and command line, which most of us are not, how do you write a test driver that enables this automated testing to work? How do we specify the structure of inputs, right? So how do we specify good generators for inputs? That's a big challenge. It even came up as a question. How do we know whether we care about these bugs? So going forward, I'm kind of interested in solving these problems around fuzzing to kind of enable these algorithms, which are pretty robust, to be used more broadly. So that includes things like automated fuzzing infrastructure, leveraging human insights, understanding it a tiny bit more formally. I'll talk a bit about some past and current work in this. So I did some work at Google, as an intern at Google on the first thing, on fuzz driver synthesis. So essentially, these were cases where programs did not have an entry point that took in a single file. And we built a tool that did some static analysis and then did a whole bunch of stuff, put it in a human presentable UI to decide the new fuzz targets. The details of that aren't too important. The takeaway is a little more important, which is that without improving the fuzzers themselves, just by improving the breadth of code that could be tested with them, we enabled over 150 security improving fixes in open source software. So without actually improving the search algorithms themselves, just by making them more usable by different types of tools, we got huge payoffs. Some current work that's kind of similar to that is, so I mentioned I had that slide where the sad emoji didn't want to write a generator. So what says that it can write a bunch of code now is GPT-3, like all these large language models. So we're looking in this project at ways, so even though people might not like to write generators, but there does exist a lot of documentation for a lot of these functions that are provided by, say, Python or different libraries. So we're looking at ways of using that natural language documentation to generate these kind of property-based generator tests automatically. And there's a lot of the research questions here actually come of like, how do we measure the goodness of those random tests? Because typically we assume they exist, we're not generating. So how do we know that the large language model is actually generating something that's relevant at all for testing software? Yep, and I'll leave more time to questions rather than get into examples of these projects. But if there are questions about those, I can talk about that. At a high level, what I talked about is I did my whole spiel of tests are good and you should write tests if you can. It's actually pretty easy to write this sort of, like random fuzzing loop into code if you want to make your tests much more robust. I talked a bit about these cool new automated testing algorithms that can perform way better than should be possible with random strings. I talked about some open problems that I'm currently working on, and that's kind of my big takeaway of leveraging the strength of automated testing, and I'm happy to take any questions. Thank you.
If there are any questions on Zoom, if you can raise your hand on Zoom or add into the chat, and I will call on you if there's any questions to press. Sure. And no, repeat.
Yeah.
So since you haven't talked more about leveraging
yeah. Right. Yeah, so the question was about using large language model to generate better tests. And what are we learning from the documentation there? And essentially, so these, the main thing we want to get at is, for the sorted things, we had encoded formally what it meant to be sorted. So we're trying to see whether we can extract from the documentation, like, can you give me properties like that of like, what does it mean to, like, does the documentation specify some things that should hold before you call this, or something that should hold after you call it? There are cases where that's more obvious than not, like in NumPy, where they describe kind of math and natural language. The large language model might be able to extract that math into code. So that's still an ongoing project. So still kind of seeing, but I think there are good results from kind of extracting, what are the kind of properties? Like, first, give me this natural language into the properties that need to hold, and then turn that into code. I don't know if that answers the question. Yeah, so then the question is about, do we need to manually evaluate the quality of the generated tests? So the paper is kind of about how can we build an automated pipeline that we trust, and there'll probably be some manual evaluation in that, but there's other things we can do, like we would like it to fail if it fails on every single input, it's probably like either there could be a really fundamental, this is really hard, this is impossible to determine automatically. If you use a large language model to generate a test like this, and it fails on every single input, does that mean the large language model was right and your code is wrong and every single input fails? It might. But because it's also really common that the large language model might do something wrong, we can't, and that's going to be like way too much data to send to the developer to check. We're going to have to assume that like maybe we're just going to look at the ones that either don't fail or that fail like 1 in 100 or something. So I kind of lost whether I was answering the question properly, but you were asking how do you evaluate these, and that is the whole difficult thing. So in the earlier work I had on this, that's why we relied on making a user interface that essentially surfaced the results to a human that would end up checking them. And in that case, that was still better than the human having to write everything from scratch. But yeah. Yeah.
So how big the case that you are
Mhm.
in the process of it?
Right.
It's exactly helping you, for example, in the merge stuff.
Yeah. Yeah.
So you let the net.
Yeah.
Of the vector.
Yeah.
To vary.
Yeah. Yeah. Yeah.
So it's kind of like giving the sense that this might be where that's coming from.
Right.
If you have audience,
Right.
then it might go.
Right.
So when you're designing that, you may kind of like do this. Okay, this is where it might be the place.
Right.
So,
Right.
like, it's curious,
Are you asking like whether are you asking whether tests in general find things that fail, or are you asking whether if you have a specific change, can you use that change, that information to test better? Is it the second thing? Yeah, so okay, so essentially the question is like, say in my example where I changed from length of the list to whatever times 2, I would kind of expect that to be particularly buggy. So that's actually, I don't actually have a good canned answer to that. There have been some research. This is actually something that I have a master's student who's going to investigate as to whether there have been some research papers that have built tools that are targeted to, like, given a change, let's target the input generation to that change. But whether those tools actually work better than the general purpose ones, we don't totally, like, that hasn't necessarily been measured at a large scale. Yeah. Yeah. That's.
Are there, like, with the algorithm,
Yeah.
nuances that make them different and implement across different languages? Like, are there things where it's less efficient to use one language or?
So the question is about the efficiency of these different techniques over different languages, and are there nuances there? So the reason I started with random testing is because that's kind of the one that's, well, unit testing and random testing are quite reliable across languages. Like, it's quite easy. Like, I mean, I can write up, okay, I have a PhD in this, so maybe this is not a bar for quite easy, but like, I can write up a random test thing in one line, in one file of Python, or probably most other languages. So that one is kind of like, it's more reliant just on like, how long does it take to run a single input? That's a little more predictable. The fancy stuff that uses the feedback, that gets super complicated for different systems. And it's actually really interesting. So I'm a software engineering researcher, and there's a whole branch of software engineering that had studied, like, called search-based software engineering, that was studying a bunch of search algorithms, like simulated annealing. I don't know if they were using MCNC, but like, they were like a bunch of like kind of mathematical search algorithms to solve similar problems to this. And that had limited, success in terms of actual adoption. And then essentially you had these security folks who like really, really hacked into all the performance details, and they're not proper simulated annealing algorithms, but they kind of have this feedback thing. And then it's only after really hacking into all the performance details were they actually able to make these tools practical. So for the kind of random unit testing that is quite flexible across languages, I would not recommend rewriting one's own kind of feedback loop driven thing. Yep.
Question for folks on Zoom. Okay, this is us. I like the concept of genetic algorithm selecting good test examples.
Right.
How would you report to an LLM generator that some examples are good at reaching of the code? And we might end it after this, seeing as we're at 4:30.
Okay, question, how might you use it sounds like something with the genetic algorithms and using the LLM to tell it to target different parts of code. There's probably some works that I haven't kept up with on using LLMs to target different parts of code. I had work using LLMs that was just targeting a single function. So I just asked it to generate a single function. So I'm not sure how much success you would have. Yeah, kind of an area of research. Maybe there is a paper that does this. But the whole idea of prompt engineering and how do you tell the LLM to target this specific thing? I've used target specific functions that worked fine. Target specific lines of code might be a little more difficult, but I think it depends. It really depends on the complexity of the code you're testing.
So it is 4:30, so we should just be respectful of folks' time, but just say thank you very much again for a wonderful talk.
Thank you.